Welcome back from lunch. My name is Jessica Dunn. I'm a senior analyst at the Union of Concerned Scientists, and I'm just moderating this session. But I get to introduce this fabulous line of 4 speakers this time. And we will be, or they will be talking about solution pathways to effective repair, reuse, and repurposing. So you were presented the kind of issue statement with the last 2 panels, and this panel will really be looking at solutions. So our first speaker is Omar from, oh, sorry, we're having a technical issue. Hard enough. Can we trade microphones? They're not able to. Oh, they can't hear me. Do I have to say it all?
You could try, but
I'm just kidding.
yeah, no.
Okay, is the microphone working online? Yeah? Okay. No, it's all good. So this panel, I'll just kind of restate, is solution pathways to effective repair, reuse, and repurposing. So this is really presenting some solutions to the problems that we've heard about in the last 2 panels. There's 4 speakers here, and the first one is a Stanford student, Omar, who will be talking about electric vehicle battery disassembly.
Thank you. So my title is Electric Vehicle Battery Disassembly. So the 3 main topics I want to talk about are the steps for disassembly, safety and technical challenges, and the environmental issues. All right. So before the process of disassembly, it's important to have 2 key components, instruction manuals and data. Currently, instruction manuals are considered proprietary information and are not readily available to recyclers or technicians. And as previously mentioned, to obtain information of the battery, such as the state of health, this requires sometimes using some ports and also practices on obtaining the data that require key and are extremely complex and are not readily available. For the actual removal of the battery pack, select EV manufacturers sometimes require the complete removal of the vehicle's interior. So this new design is being used as it allows manufacturers to more efficiently assemble the vehicle. And so this includes having sort of fixtures such as the seats, the carpet, and some other fixtures on the sides to be part and mounted onto the battery pack. So removing this requires removing the top and then lowering down the battery pack. Second, you now have to drain the coolant. And as previously mentioned, there's important safety equipment and precautions that are needed to take to drain the liquid coolant and also recycling the liquid coolant. And then disconnecting any connections. So now you have to disconnect any high voltage connections that are connected from the battery management system, which is the computer on board the battery pack, to the actual vehicle. Once you are able to release some of these bolts, the weight of an average battery pack can weigh up to 1,000 pounds or more, and it can pose a danger for the removal. And so there's specialized parts and tools needed to support the battery pack and remove it from the underside of the vehicle. This would allow technicians to move it down and move it to different locations, given the weight of it. Once this is now able to be removed and worked on by technicians, then you need to remove the protective covers. And sometimes this requires unbolting over 80 different screws that are holding down the cover. And once this is done, now you have the sort of possibility of destroying any covers. So now you have to sort of pry on the battery pack to split it open, as it sometimes is being held by epoxy or glue and other covers and protectors. So these images kind of highlight what you might see in a battery pack. And so you have the housing, which will hold everything together, then the battery modules, which will contain the battery cells, and the battery management system, which is essentially the computer that communicates with the hardware and the software. The second image really shows the different types of covers, the seals, the brackets that hold everything into place. And so you can see where the bolts are and how complex the system is just to hold the battery modules together. Now, if you're looking for cell extraction, you need to now remove the module from the battery pack. And so this requires safety gear, including eyewear, high voltage gloves, grounding mats, and multiple technicians to be readily available in case of any, issues. And so without the information of the battery, like this health or the condition of it, sometimes the contacts can hold voltage. And so this is particularly dangerous for technicians who are working, around these high voltage points and can touch the terminals. Now, if you're going for further cell level disassembly, it is seen with the cells that you have sort of a cover and like um, compounds that are holding it together. And essentially these kind of glue the cells together. And so if you wanted to remove an individual one, you'd have to sort of pry, or there's different methods where you spray high pressured air to like break down the compounds to be able to extract one singular cell. Safety and technical challenges. So currently there is not really a focus on designing for disassembly. So for many EV manufacturers, the process of battery disassembly looks completely different and ranges greatly between even just vehicle model. And then we have adhesive and proprietary tools. These ultimately prevent and deter any repair and leads to the destruction of the battery casing to even access these these materials such as the battery module and other hardware. And so, as I was mentioning, when technicians lack the parts or the manuals, it increases the disassembly complexity, and this ultimately deters proper recycling and causes danger, as prying on the battery can lead to accidental punctures and cause thermal runaway. So, in this image, one of the issues is mechanical. So if you, for example, puncture accidentally, it can cause thermal runaway, which then causes a reaction where the battery pack can be set on fire, and that just is extremely just damages the complete system. Environmental implications. So beyond the battery pack, anti-repair and disassembly policies sort of have deterred proper recycling and are creating more waste, as technicians now, will get an influx of cars, and the way to disassemble and extract the battery pack, the module, or even cells will look completely different. And so this is something that is obviously going to prevent the proper recycling of, a lot of vehicles, especially because they range in variety. And this will prevent battery modules from being repurposed and having the secondary life applications that we will further be exploring. Thank you for listening, and yeah.
Thank you so much. And what you're going to school for environment or electrical engineering? Cool. When do you graduate? 2026. So he'll be on the job market soon. Um, next up, we have a presentation from Daniela, and she will be presenting on EV battery repurposing.
Oh, is there a clicker? Oh, well, I'm here.
Hello, today I will be talking about electric vehicle battery repurposing. So I'll start by just defining repurposing and second life, which we heard about a little bit earlier by another speaker, and then go through the general steps of repurposing, and then describe some potential applications of repurposed electric vehicle batteries, and then end on some recommendations moving forward. So defining repurposing and second life. So throughout the life of an electric vehicle battery, the lithium ion or throughout the life of an electric vehicle, the lithium ion battery inside goes through many different charging cycles. It experiences extreme temperatures, and then it just ages over time. And all of this contributes to degradation of the battery, which shows up by having a shorter driving range and also longer charging times. And then at about 80% of the battery capacity, it will be then deemed at end of life. Although, as we spoke about earlier, this could change depending on the driver's original wants and needs. But at about 80%, it's considered end of life. And in this case, it can no longer support a vehicle, but the battery still has a lot of potential for other applications, such as microgrids, energy storage systems, and EV charging stations, which I'll go into a little more detail later on in the presentation. And in giving an EV battery a second life, it reduces hazardous waste and also saves material and energy compared to the recycling process. And this also has broader environmental justice implications. So it provides an alternative to mining precious metals such as lithium, nickel, and cobalt. And these are often mined from global south countries where there are less environmental and social protections, which is in a process that negatively harms vulnerable nearby communities and also natural resources. And in addition, repurposed EV batteries can provide energy storage options for renewables such as wind and solar, and improve electricity and energy access for the approximately 746 million people who don't have energy access today. And lastly, it can provide backup energy storage for low-income people who do not have reliable grid connection. So next I'll go into some of the repurposing steps, and some of these steps may overlap with one another, but this is just a general guideline to go through. So a manufacturing facility for repurposed EV batteries first needs to get certification, and then there is a long evaluation process of that original EV battery to assess its state of health. And then from there, you can evaluate the battery's viability for a second life, decide on a configuration. There's 3 different configuration, stacked battery packs, and then refurbished modules and refurbished cells. And then you disassemble and reassemble the battery in a new configuration. And as we were speaking about earlier, this disassembly process is very involved. And there are some worker safety issues, especially when paired with lack of information and policy surrounding electric vehicle batteries. So first, the facility that is repurposing an EV battery must be certified by UL 1974, which is right now the only test standard used to certify EV batteries for second life. And this involves assessing the process for sorting and grading battery cells, packs, and modules, assessing the process to identify the battery's continued viability, and rating mechanisms for continued use. And there is a really high barrier to entry. To just get a copy of the evaluation standard costs $500 to $900. And there are no standards to, or no policies to standardize repurposing. So all of these different, there's a lot of variety in all of the different manufacturers of EV batteries. And because of that, it's really hard to standardize the processes that it takes to repurpose these batteries for a second life. And this leads to a lot of unclear criteria and standards. And so next you need to have a thorough evaluation of battery health in order to measure the EV's viability for repurposing. So this involves information such as the distance driven, age of the battery, charging and discharging rates, and the state of health. And a lot of this information can be found while the battery is in use during the car's first life. However, for third-party companies trying to repurpose electric vehicle batteries, this information can be really difficult to access. And so for these third-party companies who aren't the original manufacturer or original owner of the vehicle, a lot of times they need to test the battery pack through capacity and internal resistance tests, which require workers to monitor a full charge and discharge of the battery and can take up to 2 days. But right now, there's also some startups who are working on speeding up this process through their own proprietary software, and Zora will be talking about this a little bit more in her presentation next. And so next, there's 3 main configurations of repurposed electric vehicle batteries that I can speak to. So the first is refurbished battery packs. So this is when the entire battery pack is connected in parallel to other battery packs to create an energy storage system, and this requires the least amount of disassembly. But some problems with this are that uh, the battery packs need to have similar characteristics with one another as described in the earlier evaluation stage. And they also are only going to be as efficient and good as the worst battery pack in that connection, if that makes sense. And next, you can also refurbish individual modules. And these are tested, the individual modules are tested for their performance and then can be swapped out with one another and put back together to create a new battery pack and system. And this is really good for high energy demands, but it's also really flexible depending on the needs of the final configuration. So some benefits of the module are its flexibility, its easy serviceability, scalability, and reliability. And then lastly, you can refurbish cells. And this requires disassembly all the way down to the cell level, which takes a long time. But then these individual cells can be configured into new modules and systems. And there's a lot of flexibility in this process. And it's also really good for like smaller electronic devices because of their size and also because the best cells can be chosen and used. So they're a lot more reliable. And then, but this process also generates a lot more waste as a lot of the parts of the battery are no longer used again. And then as an example of a design that is not necessarily designing with intent for repurposing is Tesla's battery pack, which isn't divided into modules. It just goes straight from the battery pack down to the cell levels. So in this case, the battery pack configuration would be better for repurposing. And it's also just an example of how intentionally designing for repurposing can have a big impact in this, a negative impact or a positive impact when it comes to electric vehicle battery repurposing. And finally, I'll go over some applications. So one main application for EV battery repurposing is microgrids, which are small scale grids that can operate independently from the grid in an island mode or can also be connected to the grid. And they really increase reliability and resilience for communities, especially when they're paired with solar energy or wind energy. And this can be really helpful for rural communities or communities that don't have grid access. So an example is a startup called Moment Energy, and they use Second Life EV batteries when connected to solar for microgrid storage in British Columbia. And another application is I found a paper about Second Life battery systems for affordable energy access in Kenyan primary schools. And they found that Second Life batteries were viable and cost competitive compared to new batteries for school electrification in Kenya and provide the same benefits while reducing waste. And next, there's battery energy storage systems. So these could be at the pack or module configuration style, and they're really useful, especially when paired with renewable energy sources such as wind or solar, and they can store energy that isn't available at all times of the day. And they can also be used for residential storage, grid stabilization and support, or backup power system for improving resilience on an industrial or utility scale. And one of the main aspects of an energy storage system is called peak shaving. And this is a process that charges the battery during times of the day when demand is really low, and then discharges the battery when demand is really high, as seen in the graphic. And this can improve overall grid resilience and also save people money, because when energy demand is really high, it costs a little bit more. And this can be done on a residential scale or all the way up to a utility scale. And this is really compatible when paired with solar, because solar charging, they can solar charge during the day when there's all the sun out and all of that energy is available, and then discharge that energy in the evening when there's no more sun. So another application is for e-rickshaws or forklifts, which is in the manufacturing industry. And this would use the module configuration, because it would have to be a lot smaller and lighter. And this is a situation when weight is really important in the configuration. And also EV charging stations. And these would also be able to utilize things like peak shaving as well, while providing energy storage and charging. So lastly, I'll end with some recommendations. So standardization, because this is a relatively new space, there's a lack of standardization across policy and processes. So policies relating to warranty, insurance, ownership of batteries, access to battery data, and permitting are all often unclear or non-existent or really difficult to find. And although there's general steps, there's no specific processes for repurposing an EV battery, and they kind of vary depending on the type of battery, access to proprietary software, configuration, and application. And there's no standardized process for deciding when to repurpose versus when to recycle. And next, design for disassembly and repurposing. I think in our previous presentation, we really learned how difficult it can be to disassemble a battery with all of those specialized tooling and adhesives and all the work that you have to go through to get down to the pack, module, and cell level of that battery. So specifically designing with the intention of repurposing and disassembling those batteries can go a long way, and it can make it a lot safer, faster, and more accessible. And next, access to information. So through making information like the state of health accessible after the first life of the battery, it can speed up the repurposing process for third parties, and also increase accessibility and safety. And then lastly, safety. So it's currently really difficult to find safety information for specific processes like discharging the battery, disassembly, and running specific battery tests. So especially for energy poverty areas working on repurposing electric vehicle batteries who may not have access to this UL 1974 facility certification, there should be some clear safety information and guidelines for all steps of the repurposing process. Thank you.
Thank you, Daniela. Wow, we learned a lot about disassembly and about repurposing, the processes there are, the big barriers, right, that we've heard about also in the other presentations, and some very clear solutions to making this a more efficient process. And Zora with Rejoule is gonna spell out some more solutions to testing state of health and to increasing repurposing.
Thanks, everyone. I'm going to stand because I just had lunch, and I don't know about you, but I'm feeling pretty full. So Rejoule, our goal is to maximize the value of every battery. And I've broken this presentation into 3 short parts. The first is just an introduction about the company and our solution. So Rejoule has raised over 20 million in funding, and most of that actually funds us not only testing, but actually deploying used EV batteries into second life applications. So some of the things that Daniela just talked about, we are actually doing with government funding. We were founded in 2017, and we're based in a tiny little city called Signal Hill, which is near Long Beach in Southern California. And we are currently powered by over 20 Rejuligans. And I proudly came up with that term. Yeah. And we have paying customers all over the world where we've deployed our technology. And with that technology, our customers have tested multiple battery types. You can see some on the screen here. And we also have some great partners that help us get access to more and more batteries so that we can increase the database of batteries that we can support through our model over time. One that I would like to highlight quickly is the Automotive Recyclers Association, also known as the ARA. We actually just published a white paper with them talking about why it's critical to test EV batteries across its lifetime as we transition from ICE to electric vehicles. In a future slide, I'll have a QR code that you can scan for our website, and you can download the white paper there. Would love to hear feedback on the white paper. The reason we exist is the fact that there is no fast and easy way to test batteries today. I think that was one of the questions from the audience members, so I'll talk about how difficult that is right now. Some of you may be thinking the manufacturer has to know, and that's what I thought too until my co-founder called me and told me they have no clue. And part of the problem is because they're using lab-aged models to do these predictions, but they're not performing actual tests once the battery is in the field. The other one is cycling. This is where you do a full charge and discharge. And unfortunately, this is the only consistent industry standard around the world. But as you can imagine, this can take hours per battery. Even for one of our customers that has a small forklift battery, that whole process takes 4 hours. So what Rejoule offers is a much faster and equally accurate way to test this battery. Our test takes only 10 minutes, but we've consistently been able to deliver 98% accuracy as compared to the industry benchmark. And another thing that we're really proud of is the fact that this has been designed so that it's so easy to use that anybody can be trained to become a battery technician and get that initial diagnostic so that we know if the battery is good enough, needs potential repair, or should be recycled. And of course, our solution can work with any battery type. And what exactly do I mean by that? I want to use 2 examples from some early popular EVs, the Nissan Leaf as well as the Tesla Model S. So you can already see on the screen that their cells are enormously different. The Nissan Leaf uses LMO pouch cells, whereas the Model S uses cylindrical NCA. From there, their modules are packaged differently, and then the packs that go into the car are also done differently. The great news is that Rejoule can test at every single one of these form factors across its entire life cycle. And here's a quick 1-minute demo of our current solution. I need to click here. So this software platform. So we're actually able to monitor everything remotely. Once you log into our software platform, you would start a test by creating a battery ID so that we can show the history of that battery over time and also choose which device of ours you're running this on. Once you start the test, you can see that we immediately start plotting the results in real time. Our test is based on electrochemical impedance spectroscopy, which is a non-invasive test. And don't worry, I won't quiz you on that later. But the important thing is here, you see that there's a grade for this battery at the end. And that's really the key that our customers want. They don't need to know the science behind it. They just need to know, is it good enough to stay in the car? Can I repurpose it? Or should this be recycled? All right, here we go. All right, so part 2, how do we try to maximize the value while the battery is still in the car? So here is the link to the white paper, so feel free to scan the QR code or come talk to me afterwards. But you should be able to download a copy of the white paper. There should be a banner at the top of our website for you to be able to do that. But I cover a lot of the topics in this talk today. So first, I want to highlight some of the challenges, 3 of the challenges that we cover in the white paper. There's many more. And some of the ways that we actually help to address these challenges. So as most of you may know, there's already a shortage of mechanics working on automotive vehicles. On top of that, there's even fewer that can actually work on a high voltage battery. The problem is, and actually a very practical one, from all the repair shops that I talk to, the managers are not going to send someone who's never worked on a car to work on a high voltage battery and get training for that. They're only bringing in their master technicians who already know their way around the vehicle. So they're only learning how to work with the battery, not how to work with the battery and a vehicle to begin with. In fact, when I ask them if there's places for them to get training, this is another problem. If you go to a community college or public institutions, they're only providing theoretical training, but no hands-on training. The only places that I've found that have hands-on trainings are private institutions like UTI, which can cost $70,000. So this is an issue. This is a huge issue because if your average person cannot afford to even get the training, how are we going to service these vehicles? And that's why we're so proud that our device is so easy to use that in some cases, once we've trained our customer how to use it, at the end, they say, that's it. Another challenge I highlighted earlier was that the battery management system is unreliable. I'll just give you one simple example from one of our customers. This is a major bus and trucking company. And they told us that they decommissioned a battery from one of their buses because the system told them it was at 30% health. And at that point, it's not even good enough to be repurposed. But they actually had the tools and resources to perform that cycling test, which took them 10 hours. And they found after 10 hours that the battery was actually at 90% health. At that point, it could have stayed in the car. But once you've already taken it out, it's very costly to put it back in because there's safety risks involved now. And in some cases, like Omar talked about, if they had to take certain components apart, they're not reusable. And also, because EVs are still relatively new, there's also very, very few supply of recycled parts. So when we're talking about doing a repair, this can be really cost prohibitive if you're always buying new parts from OEMs. And this is also very important because most vehicles on the road are actually bought used. In fact, I think the number is about 75%. And so if we're talking about someone that's buying a used EV and finding out that they have a $25,000 repair bill just to replace the battery, that completely eliminates the affordability. And to me, that hurts the true mass market adoption of EVs because if we're only selling new EVs, we're not really solving a sustainability problem. So in order for us to think through repairability, this is actually a material use hierarchy that was developed by Argonne National Labs and the ARA on the far right there. They basically define what's the most preferred outcome for an EV battery down to the least preferred. What Rejoule has done is define based on the state of health how this might fit into the hierarchy. And obviously we enable that much faster test so that you can quickly identify where on the scale the battery belongs. And oftentimes this is based on what is the best environmental impact. And usually that is also associated with the best economic impact. So hopefully the incentives are actually appropriately aligned so that we encourage reuse versus straight to recycling or disposal. So basically the key here is that knowing the state of health is critical to enabling a more circular economy. Some of the recommendations I have on the screen, everybody else has already talked about, so I won't belabor the point more. But one thing I do want to quickly touch on, especially is designing with the end in mind. Daniela talked a little bit about the Tesla structural battery pack. One point I want to add about that, because I'm so against it, is the fact that because you have the entire structure of the battery pack as part of the vehicle, if there is a fender bender in the wrong place, you can end up having to replace the entire battery pack, which can cost upwards of $25,000. I've heard quotes as high as $90,000 just to replace the battery pack. That's not even the vehicle, that's just the battery pack. Exactly. Yeah. All right. And then on to part 3 of the presentation is really how do we deploy second life batteries once they're no longer good enough for the road, but still have a lot of life left. So this is one of my favorite quotes, is that used batteries are like a box of chocolates. You never know what you're going to get. And so this means that you have to test every single one if you want to repurpose them. So as you can imagine, that sounds incredibly costly and time consuming. But obviously with Rejoul's solution, we're hoping that we can actually enable and speed up this process and encourage reuse. Some other recommendations we have to lower the cost of repurposing batteries so that it stays competitive with new ones and so that there is that financial incentive to do so is to reduce the amount of manual labor. So basically, to the extent possible, if you can repurpose at the pack level versus module or cell level, you save in that very expensive disassembly. Another thing about disassembly, because I have actually personally helped my team do some disassembly for these packs that we've received, is that it is incredibly dirty. So if you think about trying to automate this process and is it dusty, can the machinery handle it? And on top of that, can the humans handle it if they don't have the proper PPE? On top of that, you can't actually, in my opinion, I don't know if there's a way to completely automate this, because if you're talking about a used battery pack, there's going to be damage that is inconsistent. We actually have on our wall of fame the top half of a hammer because we were trying to remove a screw, and basically the handle part basically fell off because we weren't able to unscrew something that was pretty much welded in because it hit a bump on the road of some sort. The other aspect is to reuse as many of the components as possible. So we're not just talking about the battery, but if you think back to Omar's presentation, there's the casing, there's the cabling, there's the covers. All of that, as long as it's not damaged, was designed for that battery. So why not reuse it? Because those costs can really add up. A key one that I do want to highlight is encouraging the reuse of the battery management system, because those can easily cost $1,000 just to add on to a new one. So if you can reuse the old one, that is highly encouraged. In many cases, unfortunately, these are seen as proprietary. So many times the OEMs actually ask you or ask the companies that resell their batteries to remove the BMS completely. Luckily, in some cases, we were able to get it back from them, but that's not always the case. And then a little bit of self-promotion here. Obviously, leverage Rejoul's tools and expertise, not just for us as a business, but we've put a ton of information online in our blogs that I will also talk about in a little bit too. But some of the ways that we have helped our customers, this is a case study from a major automaker that we worked with. And we were helping them test their used EV batteries so they can actually redeploy them to actually pair with charging infrastructure. So we already knew that the test time would be much faster, in this case, 36 times faster. When we factor in all of the costs for us to be able to get them that fast result, including our one-time development costs to create the model, we are still 51% cheaper. We did this analysis actually for another customer that handled commercial vehicle batteries, so truck and bus batteries that were much bigger. And our cost difference was more like 90% cheaper because the equipment that they had to buy was on the order of $300,000 to $400,000 to be able to do the traditional testing. And again, cycling is an incredibly intensive process, and it requires some heavy duty equipment and certification. So with this customer that is a major global automaker, in their entire warehouse, they only had one person that could actually perform the testing. So that was actually a bigger bottleneck. Whereas with our device, anybody can be trained to perform this test. So I'll close with basically some of the blogs that we have that also talk about some of the other challenges for repurposing. You just need to know to look for this title at the top, which is the obstacle course on the path to repurposing used electric vehicle batteries, to learn more about some of these topics that I think Omar and Danielle also covered too. Thank you so much.
Thank you, Zora. I do want to emphasize some points that she brought up that are really important. Knowledge about the state of health really dictates if the battery is going to be repurposed. It dictates the information, it dictates how much it would cost, and being able to give that information to the people that are actually disassembling that battery can really open up the market. So super exciting. Every time I hear about Rejoul, it makes me a little less sad about the future of used batteries. So I'm going to pass it over to Lean to give a presentation about battery labeling.
Um, so as the fourth speaker in this session, I will be brief and to the point to talk about the importance and the potential of digital labeling. And often maybe you've heard of something called of a battery passport. So I'll touch briefly on three things. One, the momentum on battery passport mandates, the type of information that's being proposed today to be included in a battery passport, and then what are some of the key first list of questions of the many and long list of questions that we can have around access to information on that. So yes, what is a battery passport? It is a digital identifier that contains certain information on the battery's health, environmental, social, and governance performance, and manufacturing history and origin. It's effectively a kind of a digital double, stepping on, a digital double of the battery's information. And it's been often most of the discussion is really the importance of the battery passport for responsible sourcing of the metals and the materials in it. So here we're just going to put a little bit of a different spin on the role that a battery passport can play. So Meg at the beginning of the day put out a delightful question of the trade-offs between repurposing and recycling. And here in this diagram that we hope makes sense to you, we see, so here, this is the bubble of raw material mining, the extraction, right? That then these materials go into the cell pack manufacturing. And you see a dotted circle here. So today, most of the recycling that's happening is you're taking, during the manufacturing process, it produces a fairly high level of scrap. That scrap is then being recycled and put back in as secondary raw materials into the manufacturing process. And when a battery pack is manufactured, under various directives that are coming on the next slide or the one after, a battery passport is created, right? So beyond just a label, we've seen lots of pictures today of lead acid batteries, right, that have labels. So beyond just a physical label, it will have a digital label with a whole lot more information. And so then the battery goes in the vehicle. And we've been talking today about all of the, if you can see the tiny font, it says repair, refurbish, and reuse. So really this is meant to amplify and highlight that that use should be as long as possible. And then we have what we called a little battery passport health check, where you go to the doctor, or you can consider it a traffic cop. The idea being that enough information, the right type of information accessible to enough people, the right people who need it, should be able to make that decision point, right? Of, is that battery going to go all the way into the end of life, considering it's spent, and be recycled? Or does the little health check say, actually, it should be routed to the one of many possible second lives? And that ties into what Zora was just mapping out as well in the material use hierarchy, that rejoule testing can look at the state of health to make that decision. And so this is that trade-off, right, of that Meg was pointing out, of the that we have recycled content requirements today, right, that would drive a battery to skip the second lives and go immediately to recycling and back into the process. And so what is then where do we see initiatives coming for a battery passport? It's in the EU Battery Waste Directive that was entered into force last year. That one will start requiring battery passports. Implementation will start sometime this year, but I don't recall off the top of my head the exact date that the battery passport itself will be mandated. But all vehicles in the EU, electric vehicles in the EU, will require a battery passport. California and 17 other states have adopted a rule mandating battery passports as of 2026. Those are all at different states of enforcement, but there are certain commitments and adoptions towards a battery passport at the state level. And then we've also seen certain calls for that to be adopted federally as well. And then there are many industry initiatives, such as by Ford, in a group of EU industry, auto industry makers are gathering under Battery Pass. And then there's the Global Battery Alliance, GBA, that is developing a global framework, rule books, as they call them, on a battery passport. And you see so many of these initiatives underway. And the question is, what is inside? And we don't really know. Sheila and I have had calls with Global Battery Alliance trying to discern what on earth is in the battery passport, and it's fuzzy, and they're still defining it. Here, I'm giving an example of what's in the EU Battery Waste Directive. So in the column on the left is what they consider publicly available information about the battery. So that's the label, the sticker that you see, the same, sticker information that you see on a lead acid battery. Where was it manufactured? What is it? On what date? What is the hazardous substance? What's added to that new is the composition. So it should be publicly available. What is the battery chemistry, the carbon footprint, the sourcing, right? And then the responsible sourcing thresholds that it meets, the rated capacity, and its expected lifetime. So that's what's publicly available. On the right hand, we see what the EU defines as the data available to persons of a legitimate interest, is I think the term, and I don't believe that has yet been defined in implementing regulations. And that is more what we've been talking about today, dismantling. Here we get detailed battery composition. What's publicly available is only, more generalized battery composition. We see replacement parts, dismantling instructions, what are the replacement parts, and the safety information. And then finally, for persons of legitimate interest, also have access to the state of health, performance, state of health, history of use, and negative offense. But this then, tying back to Zora's presentation is how is this determined and how accurate and reliable is that information that's collected in the battery passport? So I'll wrap up on this last slide, which is the many questions that we have on how the battery passport meets the thresholds that we know from the right to access to information. What is the data? Exactly. I listed on the previous slide a bunch of different categories, but there's a lot more detail and verification and cross-checking that is needed of what is provided in the Battery Waste Directive with the rich content and aspects that have been highlighted in the room. Even just on the question of proprietary technology is a major red flag. Which users? Who has access? Is it any consumer? Is it an independent automaker repair shop? Is it only the manufacturer? Again, the proprietary nature is a big red flag. Then this battery passport information, it's available on which platforms, which devices, in what language to have access to it, at what cost to access that information. And then a critical one of who owns and updates the data and what kind of barriers can that present. And this is a first suggestion of questions that I think we'll continue to add more here. So that is a quick primer, if you will, on the opportunities for a battery passport to be able to support second life applications. And I'll wrap up there. Thank you.
Thank you. I think do we have time for questions? I don't know what time it is. Yes. Okay. Any questions for the group here? Yeah, go ahead, Perry. Oh, I have to give them I can do that.
Yes, for Omar, I was curious as to the role of the cooling system and why draining the cooling system is required. I was confused about that. Is this something that goes around the battery?
Oh, like. Yeah, great question. So I think the reason what like I included the cooling system. So the cooling system will essentially, as I was mentioning, there's a large variety of battery packs and the way they're designed, the way they're cooled. Like there's like for the foam that I showed in the cells, sometimes they use that as a method of actually like serving to cool down the batteries and make sure they don't get hot and cause thermal runaway. But I included that just to show that this is a factor that you'll have to drain out, and this creates waste, right? You're not gonna like there's impurities, and once you take it out of the vehicle, like you're going to have to recycle this or take it to some place that can be properly disposed of. And when you're working in other parts of the world, like the access to these areas that you can take them to probably is not as available as it would be in other places. And so that was kind of the inclusion of why draining the coolant is something that has to be done for further disassembly, and why it's important in terms of just the whole process of disassembly in general.
Thank you, Omar. Any other questions or any questions online? Oh, yes, go ahead.
Yeah, I'm really interested in the question of standardization because I can see how it could really facilitate things in terms of second life and repurposing. And I also think that one of the opportunities we have now, or we have a lot of opportunities now because design is so like malleable, it's in such change, like we can actually push industry to move in certain directions because they're not locked in. And so I'm wondering, I'm sort of like wanting to resist the idea of standardizing through policy that would lock us in. And I'm wondering if anyone's, looked at this or thought about this, like how do you create more standardization, but still leave a lot of flexibility for improvements? Anyways.
Great question. Zora, do you want to take that?
Hello? Okay. I'll try to take a stab at this. So we've talked to a few different automakers about that challenge, because even within the same vehicle, like Nissan is on its 4th generation of battery design, and there's not consistency there, which is a challenge. So I think one thing is that because it's still so new, that inherently you're going to have significant improvements. So that does pose a challenge for the earliest models. I think what is important though is really what Leon talked about in the previous one about like making information available, because if we don't know, that doesn't solve any problems. So making certain pieces of information available. So I think to answer some of those questions in terms of, okay, if we can't obviously see the entire battery management system because it's proprietary, we should be able to see certain aspects of information, and that should be standardized. In terms of the state of health, one challenge that we're constantly getting from third parties that basically own the vehicles but aren't the OEMs is they say they don't trust the data from the OEMs, but 2, if you're talking about a Nissan vehicle versus Ford versus Tesla, 90% state of health could mean wildly different things among the 3. So I think having standard language and definitions is a great place for us to get started. It's not going to help with automation if everything's different, but at the same time, there needs to be flexibility, right? Like, how would you feel if everybody's car looked exactly the same? Like, so there needs to be some flexibilities for different use cases. But I think we need to start with information sharing. And then from there, we can learn more on what's important.
Yeah, and I will also add there's no incentive right now to standardize, right? There's no extended producer responsibility in the US. There's nothing that the OEMs aren't responsible for their batteries. So there's no yeah, there's no incentive there. And there's also been discussions of standardization within California, and they've been obviously kind of automatically shut down by the automakers, right? Because of the idea of needing to innovate, which there is reason for that, but there's also, you know, that political aspect. Yes. Oh, you got it behind you. Perfect.
Thank you.
I'm like, correct me if I'm wrong, but I think I heard that 80% of the battery capacity is seen as end life for EV batteries. So I wanted some more information on that, and then just some follow up with that question. I know that there's lots of variety with the different like batteries, but if you can provide like an average estimate of like how long these EV batteries last. And then if I can add a third question, and if there's some type of like estimate of the percentage of the ones that are in the market at the moment that can be extended for a second life.
I'll take this one. So I mentioned that the EV batteries are considered at end of life at about 80%, but this number is, and this is determined by the range of the battery and how far it can be driven. So if someone did feel like they're not driving super far and they're okay with having a shorter range, then maybe the battery could go down to 70% or even less. But just the typical, just across my online research, I found that 80% is standard considered end of life for a battery. And this means to be about 8 years. I think warranties on electric vehicle batteries are generally 8 to 10 years, I'd say, but some of them are lasting longer than that. And if anyone else has information on the final question.
I can probably, yeah, and just actually onto the second point, we actually spoke to the EPA recently because they are performing testing to validate like how long should we mandate that these warranties last, and they said that they actually haven't done the hard work to see how long it should last. But I've actually read studies where even in a second life application, especially if it's much less stressful than the vehicle, which goes through shock, vibration, intense temperature changes, and like a much more difficult load profile. Like imagine like if you're carrying a load and trying to get from 0 to 60 on the freeway versus being in a stationary application, it could actually last up to 20 years, which is incredible. In terms of how many can be reused, so what we've seen because of this over design feature and like many of the batteries that we've seen are usually above 70% state of health. I didn't have it in this presentation, but in another slide I had where we were just working with forklift batteries, they had decommissioned these batteries because they weren't even going to left for a forklift application. But when we tested them, most of them were at above 85% health. So in theory, they could have even gone put back into the forklift if not used for a second life application. So I would say that that's pretty high right now. The ones that you often see fall out of that would be really warranty issues. So there's inherently a defect associated with it anyways. Oh yeah, basically a very high percentage is what we're seeing right now. Yeah, especially I think for the earlier ones, what we've heard is that a lot of the OEMs over-designed because they really weren't sure how long it would last. And then for the newer chemistries now, basically they're trying to optimize so that it's not so over-designed because it might not be reused or it would just end up going to waste. So there is some optimization, but from what we've seen, many of the batteries are basically close to that 70 to 80% state of health by the time we see it, which is it's been decommissioned from a vehicle.
Line.
All right, so we have a few questions from Christine Kubat from Recycle Hawaii. Wouldn't repurposing just end up as a dumping mechanism on rural communities and the global south? How long do the repurposed batteries last? And is there a way to test the battery management system to make sure it is still working?
Yeah, I think in terms of how long will they actually last, that's actually to be seen. And that's where a lot of the government funding is coming so that we can actually figure that out. And no, it is not a dumping ground. And that's actually one of the questions that we got from the Department of Energy, because one of the locations that we're looking to deploy long duration energy storage is in Red Lake Nation, which was tribal lands. And for us, it's like, yes, these are older batteries, but the idea behind this is completely new technology. Energy storage is still a new technology. Deploying energy storage with second life batteries is new technology, and you have to have a lot of engineering innovation to make this happen. So we're actually very excited to work with Red Lake Nation and the Workforce Development Campus to not only train, we won't be the ones training, we're working with workforce development groups to train the local community to not only do the installation, but the maintenance of these systems. So our hope is that this is basically playing a leadership role in not only enabling renewable technologies, but also enabling a more reliable grid. So yeah, I definitely don't want to think of this as trash just because it's used. It definitely takes a lot of innovation for this to happen. Did I answer all of the aspects of the question?
That's it.
Any other questions in the room? Yeah, in the back. Thank you.
Yeah, if we could just drive down to Tesla right now at the Fremont factory, what would be like a quick fix that you all would recommend to them without it like disrupting the whole design of the car?
Yeah, I mean, the first one would be the design of the car. The structural battery, yeah. I mean, like you heard me earlier, the structural battery pack, it's like I think Meg was the one or Jessica that said like they're not evil, right? Like they're doing this because it's optimized for production. It's so that they can produce cheaper electric vehicles to get out there. But the problem is that doesn't help with repairability and reusability. So yeah, for me, it's really about that. Maybe the other thing that doesn't ruin it would be sharing more information so that there can be better reusability, repairability, and then also making it more of an open market, because at this point, if they're controlling all of not only the design but the repair and also access to the tools, really it's hard for third parties to offer that service, and it becomes obviously really expensive. Like if you have a car that's out of warranty, how many of you are still taking it back to the OEM, right? Like you're going to find an independent repair shop because it's more affordable.
Yeah, in my research, I found that so once the car was essentially like in its, like you had the battery pack itself, there's like I think it's like a 5-star panel, like a screw that's Tesla specific. And so as we previously mentioned, like Apple designed their own Penelope screw, and so Tesla had the exact same thing. And so like people have been like, who are like focused on, secondary life applications for these batteries, like are reverse engineering their like screw configuration and now like have one on their site that they sell. So it's like that little decision of like putting that like some screws, scattered around the battery pack. So like you did all this work, now you have the battery pack. Oh, I've never seen this screw before. Like, now you buy it from someone else, or now you have to maybe like, drill into it, which is just dangerous. And so little techniques like that really kind of highlight how they don't want you to get into this, or don't want you to be, fiddling around with their batteries.
Thank you. I think that was our last question. So big round of applause for our 4 speakers. Thanks so much. 5-minute break. Okay, we have a 5-minute break, and then we'll come back to our last panel on policy. Thank you.